Hello and welcome. I'm Brad Ford from the Camera Software Engineering team. In this session, I'll be introducing you to camera extensions with Core Media I/O, which is a modern camera driver architecture for macOS and a replacement for DAL plugins. DAL plugins are a technology that allows you to create camera drivers for hardware that plugs into a Mac, or virtual cameras. They've been around for a very long time, since macOS 10.7. DAL plugins provide the power to extend macOS as a rich media platform, bringing support for great third-party camera products to pros and consumers. It's part of what makes the Mac the Mac. But DAL plugins have some problems. They load untrusted code directly into an app's process, making it vulnerable to crashes if the plugin has bugs, or to malware attack. For this reason, they don't work with Apple apps such as FaceTime, QuickTime Player, and Photo Booth. They also don't work with many third-party camera apps, unless those apps intentionally disable library validation or the user turns off system integrity protection. Neither of these are practices recommended, as they make the system less secure and less stable. They're difficult to develop, too. They carry a C API circa 2011, and a thick SDK of C++ helper classes for you to learn. And on top of all that, they're sparsely documented. It's time for an upgrade. macOS 12.3 introduces a thoroughly modern replacement for DAL plugins called camera extensions, an architecture that places user security first. Let's learn how it works. First, I'll provide a technology overview. Next, I'll show you how to build a camera extension from scratch. Next, I'll introduce the main classes and functions of the API. I'll explain how Core Media I/O extensions can be used as output devices. And finally, I'll cover our DAL plugin deprecation plan. Let's get started. Camera extensions, otherwise known as Core Media I/O extensions, are a new way to package and deliver camera drivers to Mac applications. They're secure. Your extension code is cordoned off into its own daemon process that's sandboxed and run as a role user. All the buffers your extension provides are validated before being delivered to an app. They're fast. The framework handles the IPC layers between your extension process and the app, with an emphasis on performance. The framework can also take care of delivering buffers to multiple simultaneous clients. They're modern. Your extension can be written in either Swift or Objective-C. They're simple. There are just a few classes to learn, a few protocols to implement in order to get up and running. The framework takes care of the boilerplate code. They're easy to deploy. You can ship them as apps in the App Store. And camera extensions are 100% backward compatible with existing AV Foundation Capture APIs. Camera extensions show up just like the built-in camera in all camera apps, including Apple apps. Here's an example of how a camera extension might appear in the FaceTime camera picker. What kind of experiences can you build with a camera extension? Let's study 3 common use cases. The simplest use is a software-only camera, such as a camera that displays color bars, a unique test pattern, programmatically generated images at various frame rates or resolutions, or a camera that streams pre-rendered content, such as frames in a movie, to test AV synchronization. The second use case is a driver for a camera that you intend to physically plug into a Mac or discover wirelessly. Camera extensions fully support hot plugging and unplugging. To address your hardware, you have a few choices. The preferred method is to use a driver kit extension, or DEXT, which runs entirely in user space. If your hardware must be addressed at the kernel level, you can use the legacy I/O video family KEXT path. Development of new KEXT code is discouraged, as KEXTs are inherently less secure and can contribute to system instability. Apple provides a class-compliant extension for USB video class, or UVC cameras. It works great for cameras that conform to the UVC spec. If, however, you need to support a USB camera that uses non-standard protocol, has additional features outside the UVC spec, you can create a camera extension that overrides Apple's UVC extension, allowing you to claim a particular product and vendor ID. If you're interested in learning more about it, please refer to the article at developer.apple.com entitled Overriding the Default USB Video Class Extension. It explains how to create a minimal DeXT bundle and which IOKit personalities keys you need to override in your info plist. A third common use is a creative camera, a hybrid between software and hardware. Your extension accesses a video stream from another physical camera attached to the Mac, applies an effect to those buffers, and sends them along to clients as a new camera stream. Or a creative camera that accesses video streams from several cameras, composites them, and sends them along to the app. A creative camera like this might use a configuration app to control the compositing or parameterize filters. The possibilities for creative camera are really endless. Now that we've explored the primary use cases, let's look at the anatomy of a Core Media I/O extension. First, the Core Media I/O part. Core Media I/O is a low-level framework for publishing or discovering camera drivers. You already know that it contains the legacy DAL API and the new Camera Extension API that replaces it. But it also contains a powerful set of low-level C APIs for app developers to find and inspect cameras on the system. Now, how about that extension part? Core Media I/O extensions are built on top of the System Extensions framework, which first appeared in macOS Catalina. It obviates the need for a throwaway installer. Instead, you ship your extension inside an app. The extension executable lives within the app bundle. By making calls into the System Extensions framework, your app can install, upgrade, or downgrade your extension for all users on the system. And uninstalling is a snap. Delete the app, and the System Extensions framework uninstalls your camera extension for all users. This delivery mechanism is approved for App Store use, making it easy to deploy your camera extension to a wide audience. To learn more about the System Extensions framework, you can read the documentation at developer.apple.com, Documentation, System Extensions. And be sure to check out the WWDC 2019 video entitled System Extensions and Driver Kit. That's it for our technology overview of camera extensions. Now, let's actually build one. Here's a quick demo of how to get a camera extension up and running in a matter of minutes. I've created a single-window macOS application in Xcode called ExampleCam. At this point, I've only added a few lines of code. The app delegate is unchanged. In the main storyboard, I've added two buttons, one to install and one to uninstall the extension, plus a text field to display status. In the View Controller class, I've added IB actions to hook up the install and uninstall buttons. These functions create OS system extension requests to either activate or deactivate the extension found within the app's bundle. At the bottom, I've added skeletal implementations of the OS system extension request delegate functions that log status. The app's entitlements file has the usual app sandbox = yes, and it defines an app group. I've only added one new key here, the system extension key, which is required if your app installs system extensions. At this point, if I run the app and click on the Install Extension button, I'll just get a fatal error, since the app is looking for an extension in the bundle that doesn't exist yet. To create and embed a system extension, I go to File, New, Target, and under macOS, I scroll all the way down to the bottom where the system extensions are located. Then I pick Camera Extension, hit Next, give it a name. I'll choose Extension. I'll make sure that Embedded in Application is set, and then I click Finish. Inside the new extension folder, I get 4 new files. The info.plist identifies it as a CMIO extension by defining its mock service name. This is a critical piece of information. Core Media I/O's Register Assistant will not launch your extension unless it's present. While we're here, let's give it a usage description for the system extension. The entitlements file shows that it's app sandboxed, and I need to ensure here that my extension's app group is prefixed by the mock service name in order for it to pass validation. So I'll copy and paste that over from the app extension to the extension's entitlements file. And that's it. The main.swift file serves as your extension's entry point and starts the service. And the extension provider.swift file gives us a fully functional camera. It contains a device source, a stream source, and a provider source. All that you need to create a pure software camera. Not a bad little template. In this file, I'll search for sample capture, and I'll replace with example cam, so that my camera's name, model, and manufacturer all have the proper name. That's it. Let's compile and run it. When I hit the Install button, it fails. That's because system extensions can only be installed by apps residing in /applications. Let's move it and try again. This time, it succeeds. I'm prompted to allow the blocked extension to install by authenticating in System Settings, where I find Privacy and Security, and click the Allow button. I authenticate with my password, and then I see that my result has changed to 0 for no error. If I use the System Extensions Control List tool, I confirm that I've succeeded, and now I have one extension active on my system. Now I can open any camera app and find and admire my work. Let's launch FaceTime. Example Cam shows up in the camera picker. Sort of looks like the old Pong game from the 70s, drawing a horizontal white line that moves up and down the frame at 60 frames per second. To get rid of the camera, all I have to do is delete the app. The system prompts me to confirm that I'm also uninstalling the extension by deleting the app. The example cam demo shows just how easy it is to make a software camera from scratch. Now, let's take it up a notch by turning that software camera into a creative camera. I call the second example CI Filter Cam. The CI stands for Core Image, a framework with all sorts of effects filters that you can apply to stills or video. To create CI Filter Cam, I began with the example cam shell, but decided to make the app a configuration app as well as an installer. I've added a camera picker button, a filter picker button, and an effect bypass button. I've also added a view for live video preview. This is a standard view backed by an AV Capture video preview layer to show you what the filter camera is doing. By unchecking the bypass button, I can see various filters applied to the video, from color effects to distortion filters. I'm kind of partial to the bump distortion. I can apply these to the built-in FaceTime camera or to any physical camera attached to my Mac. I've got my iPhone nearby, set up as a continuity camera. Let's use that. The CI Filter Cam app is nothing special in and of itself, just an effects camera app. Where it really gets interesting, though, is when you realize that the app is a front end to a virtual filter camera that all apps can use. I'll launch FaceTime and Photo Booth and make sure both of them are pointed at the CI Filter Cam. Now, as I change filters in my configuration app, every app using CI Filter Cam changes in tandem. If I pick a different source camera, every camera app picks up the change. Every button click in the app translates to a simple property call to the Filter Cam extension, telling it, "Hey extension, use this camera," or "Hey extension, use this other filter," or "this other filter," or "this other filter." Support for running a hardware camera inside your extension requires macOS Ventura. You also need to add the com.apple.security.device.camera key to your extension's entitlements file, indicating that you will be using another camera. And since you'll be using a camera, the user will be prompted to grant permission to your extension. So you must provide an NS camera usage description in your info.plist. That wraps up the basics of building a camera extension. Now, let's move on to the APIs. At the bottom of the stack are daemon processes, one for each first or third-party camera extension. Within a camera app process, there are several layers at play, beginning with the private framework code that talks to your camera extension over IPC. One level up is another private layer that translates Core Media I/O extension calls to legacy DAL plugin calls. Up again, we find the public Core Media I/O APIs that publish DAL plugins. To the client of this interface, there is no difference between Core Media I/O extensions and DAL plugins. Everything looks like a DAL plugin. And finally, at the top is AV Foundation, which is a client of Core Media I/O. It republishes DAL plugins as AV Capture devices. Contrast this with the legacy DAL plugin architecture. DAL plugins may or may not include a daemon piece, but all of them run code loaded by the Core Media I/O framework directly in the app process. This leaves the app vulnerable to malware. Camera extensions remove this attack vector completely. Your extension must be app sandboxed, or it won't be allowed to run. Apple's Register Assistant service identifies it by its CMIO extension mock service name and launches it as a role user account called CMIO DAL Assistance. Sandbox D applies a custom sandbox profile to your process. It's tailored for camera use cases. The custom sandbox profile allows you to communicate over the common hardware interfaces you would expect: USB, Bluetooth, Wi-Fi, as a client, but not a server that opens ports, and even FireWire. It also allows your extension to read and write from its own container and temp. The Camera Extension Sandbox profile is more locked down than a regular app. Some examples of things you can't do are forking, execing, or POSIX spawning a child process, accessing the Windows server, making a connection to the foreground user account, or registering your own mock services in the global namespace. If, as you develop your extension, you find the sandbox too restrictive for a legitimate capture case, please provide us feedback through Feedback Assistant, and we will carefully consider loosening restrictions. The earlier architecture diagram showed your camera extension's daemon process passing buffers directly to the app layer. There's actually one more layer of security involved. Between your daemon and the app is a proxy service called Register Assistant Service. It enforces transparency, consent, and control policy. When an app tries to use a camera for the first time, the system asks the user if it's okay. That consent needs to be granted for all cameras, not just the built-in ones. The proxy service handles this consent on your behalf. If the user has denied camera access, the proxy stops buffers from going to that app. It also handles attribution. It lets the system know that a particular camera is in use by a particular app, so that power consumed by your daemon can be attributed to the app that's using your camera. Core Media I/O extensions have four main classes: provider, device, and stream. Providers have devices and devices have streams, and all three of them can have properties. You create each of these three main classes by providing a source, respectively a provider source, device source, and stream source. The extension provider is your lowest level object. It lets you add and remove devices as needed, such as for hot plug events. It gets informed of the client processes as they try to connect, which gives you an opportunity to limit your device publishing to certain apps. It also consults your provider source object for property implementations. Here's what your extension's main entry point might look like. You create your own extension provider source, which conforms to the CMIO extension provider source protocol and creates an extension provider. To start your service, you call the provider class method startService and pass your provider instance. Extension provider implements two read-only properties that do not change for the life of your extension: the manufacturer and the name of your provider. Both of these are strings. Next up is the CMIO extension device. It manages streams, adding or removing them as needed. Your device can present multiple streams, but be aware that AV Foundation ignores all but the first input stream. When you create a device, you provide a device source, as well as a localized name, a device ID as a UUID, and optionally, a legacy ID string. These properties percolate all the way up to AV Foundation. Your device's localized name becomes the AV Capture device's localized name. Your specified device ID becomes the AV Capture device's unique identifier, unless you also provide a legacy device ID. You only need to provide this if you're modernizing a DAL plugin and need to maintain backward compatibility with the unique identifier you previously shipped. If you provide a legacy device ID, AV Capture device will use it as the unique identifier. You create your CMIO extension device with a CMIO extension device source, which may optionally implement other properties, such as device model, which should be the same for all cameras of the same model. is suspended should be implemented if your device can enter a suspended state, such as if it has a privacy iris. The built-in cameras on Apple laptops enter the suspended state when the clamshell is closed. Your device's transport type reveals how it's connected, such as via USB, Bluetooth, or FireWire. Lastly, if you have a microphone physically paired with your camera, you can expose it as a linked device. All of these properties are read-only. Next up is the all-important CMIO extension Stream, which does the heavy lifting in the CMIO extension. It publishes video formats and defines their valid frame rates, and configures the active format. It uses a standard clock, such as the host time clock, or provides its own custom clock to drive the timing of each buffer it produces. And most importantly, it sends sample buffers to clients. Your extension stream source publishes CMIO extension stream formats. Those become AV Capture device formats. Clients can read and write the active format index to change the active format. The frame duration, which is equivalent to max frame rate, and max frame duration, which is the same as min frame rate. The DAL plugin world exposes a fourth interface called DAL controls. Plugin developers use these to expose features such as auto exposure, brightness, sharpness, pan and zoom, etc. While powerful, they've been implemented inconsistently, so it's difficult for app developers to use them. In the CMIO extension architecture, we don't offer a DAL control replacement. Instead, everything is a property. You've already learned about many standard properties at the provider, device, and stream level. You can also make your own custom properties and propagate them to the app layer, just as I did in the CI FilterCam demo. Core Media I/O's C property interface uses a C struct to identify a property's selector, scope, and element. These are considered its address. The selector is the name of the property as a 4-character code, such as CUST for custom. The scope can be global, input, or output, and the element can be any number you want. The main element is always 0. CMIO extensions let you bridge your properties to the old world by coding property address elements into a custom property name. First, the characters 4CC_, then the selector, scope, and element as 4-character codes separated by underscores. Using this method, you can communicate any string or data value to the app layer. AV Foundation doesn't work with custom properties, so you must stick to the Core Media I/O C API if your configuration app needs to work with custom properties. That's our high-level look at the API. Now, let's talk about output devices. A lesser-known feature of DAL plugins is their ability to present the opposite of a camera, an output device, which consumes video from an app in real time rather than provides it. This is the O part of Core Media I/O, input and output. Output devices are common in the pro video world. Some common uses are print-to-tape, where a video signal is sent to an external recorder, or real-time preview monitoring, such as on a Pro deck with SDI inputs. One important thing to note is that output devices have no AV Foundation API equivalent. To send frames to an output device, you must use the Core Media I/O C API directly. CMIO extension streams are created with a direction of either source or sync. Sync streams consume data from an app. Clients feed your sync stream by inserting sample buffers into a simple queue. That translates to a consume sample buffer call in your extension. And once you've consumed that buffer, you notify them with notify scheduled output changed. There are a number of stream properties specific to output devices. They mainly deal with the queue sizing, how many frames to buffer before starting, and signaling when all data has been consumed. Now, on to our fifth and final topic of the day. Earlier in the presentation, I showed this diagram of the DAL plugin architecture, and I highlighted its many security problems. We've addressed these shortcomings with camera extensions and are fully committed to their continued development. They are the path forward. So what does that mean for DAL plugins? It means the end is near. As of macOS 12.3, DAL plugins are already deprecated, so you get a compilation warning when building. That's a good start, but it's not enough. As long as legacy DAL plugins are allowed to load, camera apps will still be at risk. To fully address security vulnerabilities and make the system more robust for all users, we plan to disable DAL plugins entirely in the next major release after macOS Ventura. What does this mean for you? Well, we hope the message is clear. If you currently maintain a DAL plugin, now is the time to begin porting your code to a camera extension. And please, let us know what friction you encounter. We are eager to address these issues and provide a rich feature set. We really look forward to working with you. This concludes today's presentation on camera extensions for macOS. We can't wait to see what fresh and creative camera experiences you'll bring to the Mac, and hope you have fun doing it.